is a test of lighting and exposure, and it will be very interesting to see how this looks on the playback. First, I'm going to put on my coat and try that. All right, and this will be the format of the recording which I plan to make now. What I'm going to do is first start out with my primary interest at the end of graduate school in things that had to do with radioactivity, following it up with my experiences at the College of the Pacific, now at the University of the Pacific, and with subsequent experience in being recruited for the radiation laboratory at the University of California, which then led to Oak Ridge and the exciting days there. Nothing more.
Okay.
Fine. I'm recording now. So that your voice is on there for posterity now. So this is a test to see if the audio is sufficient. I have moved the camera back fairly far because this will give me more depth of focus on the subject, and I think it will be much better if we can put the camera back farther and then light accordingly, and this will give us a more depth of focus on the subject, and I think in general a much more pleasing appearance. The main thing of it is, when we go back this far, is the audio still functioning? All right, we'll try the test now. This next test is to determine whether or not I get a better light distribution with the reflector over on the right-hand side. I think just by visual inspection, I don't think that it makes all that much difference, but I think the only way we'll be able to determine that is to watch carefully and analyze the playback to see whether it functions properly. I think we've got enough here now so that I think we can see if we've made any improvement whatsoever. This is the first test draft of the actual interview. My cut. After that brief interruption caused by my good friend Prince, I'll start this interview from scratch. Okay, let us take one. My story begins with some experiences I had in graduate school, which ultimately led me into the Manhattan project. We, as a graduate student, I did not work in radioactivity, but I did do some research work on the role of electrochemical phenomena and physical chemical phenomena and the relationship between inorganic compounds and organic compounds. So as a consequence, I did manage to get a fair understanding of the field of inorganic chemistry, which was to play a very key role in my subsequent interests. My acquaintance with radioactivity and nuclear physics, of course, grew out of the fact that I was present at Berkeley and graduate school during the exciting years when E.O. Lawrence was developing the cyclotron. And I can remember distinctly in attending one of our graduate science meetings when there was radioactive sodium produced in the cyclotron, and a demonstration was made of the speed of absorption of sodium ions into the bloodstream. In order to carry this out, a preparation was made containing radioactive sodium chloride, and the subject drank this. Of course, it was very low levels, so there was absolutely no danger. And then the Geiger counter was placed at the fingertips. And it was really amazing. I think it was something like 35 seconds after drinking this that radioactivity actually began to appear in the fingertips of the subject. So that was quite a spectacular demonstration of the early uses of radioisotopes in the field of medicine. Of course, after the discovery of the neutron and after the discovery that artificial radioactive isotopes could be made either bombarding by neutrons or by deuterons or other suitable atomic projectiles. This was a very important and very active field of science immediately after 1935. I can very early remember the discussion of the discovery of artificial radioactivity and the sensation that it made during the years approximately about beginning in 1935. Well, to make a long story short, almost immediately thereafter, I took a position as a professor of chemistry at the University of the Pacific, actually then called College of the Pacific, where I spent 5 wonderful years as a teacher of inorganic and physical chemistry. During those years, I maintained my interest in the spectacular field of radioactivity, and I made arrangements with E.O. Lawrence to obtain some of the target material that was used to hold the particular element being irradiated. In other words, whenever someone wanted to carry out an experiment, they put it in a holder, and then the particular element was then bombarded with deuterons, and then subsequently taken off the target to be worked up, and the experiments carried out, and the identification of the radioactivity made. And of course, there is sufficient stray deuterons that would hit the holder of the target, and I was able to get some of the old targets, which had, of course, iron, chromium, and I believe some of the other cobalt and some of the other materials used to make stainless steel. So consequently, there was a slight amount of radioactivity which was generated as a result of the stray deuterons hitting these targets. Of course, the radioactivity was very small, but adequate for experimental purposes. I then took these targets and dissolved them, and then using chemical separation methods, I was able to separate out several radioactive elements. And at the time, of course, there was nothing new about these radio elements, and so I was not in a position to discover any new radioactive elements. But I was able to use the fact that we did have radioactivity to use in actual experiments to determine more efficient separation methods. In order to separate out, say, iron or cobalt or manganese or chromium from this mixture, it was necessary to subject it to chemical methods, precipitate the different elements with different reagents, and then actually get other methods developed, such as extraction and so forth, so that by doing this I was able to sharpen my skills in the separation of one element from the other, which was to play a real dominant part in my subsequent work on the Manhattan Project. In order to do this, of course, you had to have a method for detecting radioactivity. And as strange as it may seem, in those days, the Geiger counter, of course, had been invented long before that, but they were quite expensive and quite erratic and quite difficult to operate. However, Dr. Lauritsen of Caltech had invented a quartz fiber electroscope in which he gold-plated fine quartz fibers. When those were electric charges placed on that, of course the fibers would fly apart, and then a scale was put in the back, and this was put inside of an optical device so that you read it by looking through the viewpiece, and then by actually timing the decay of the radioisotope, I was able to determine the relative activities. So this was a very useful tool. In fact, I have talked to Glenn Seaborg quite recently, and he mentioned to me that whereas most of the time he used the Geiger counter, he did find the Lauritsen electroscope a very useful tool. In fact, almost superior to the Geiger counter at that time for certain purposes. Well, this introduced me to radioisotopes and the actual ways in which you could use separation methods, and it was a very fascinating field. In fact, one of the things that I did at that time was to develop a method for determining the amount of sulfate in very dilute solutions. And by using radioactive chromium as a tracer, I was able to develop a rather crude method. About 15 years later, I went back in the laboratory back at Oak Ridge with the modern techniques, modern apparatus, and I was able to develop this, and actually wrote a short paper on the use of radioactive methods for the determination of sulfate. Rather, not a very significant contribution, but a very interesting one. Subsequent to that, of course, I was, and coincident with that, I was very busy with my work as a professor, and this kept me very well occupied. In fact, at that time, with the really tight budgets compared to budgets in colleges these days, we were expected to teach the equivalent of 15 lectures a week, of course, with the additional responsibility of running the examinations and tests and preparatory to laboratory work and so forth. So it did not leave me too much time for research work. However, one of the things I can remember in our teaching experience was that we would have a seminar every Monday afternoon to discuss recent findings in the field of chemistry, and for this particular Monday afternoon, I had read about the discovery of the Hahn and Strassmann in the demonstration of the fissioning of the uranium atom. And this was a very, very significant device. Here, in this one article, which did not occupy too significant space in the journal, immediately all of those of us who were familiar with the field, and this was worldwide, could see immediately this was the key to unlocking the energy of the atom, something that people knew could ultimately be done, but there was absolutely no progress in doing it in such a way that it could be practical. All other attempts to unlock energy from the atom resulted in more energy being put into it than you could get out of it. In this particular case, there was perhaps 100,000 or even an infinite amount of energy gain in the process of fission. So we spent that particular period actually discussing the implications of that new development in science. At that particular time, of course, the word fission was not used, and I have a story somewhat later as to how the term fission originated. But this was very interesting, and then, of course, within the next 6 months, articles appeared in the popular press as to the implications of this and speculation, and but sure enough, so far as scientific mention of this is concerned, this immediately dried up. No articles appeared in any of the journals, and at first there was a self-imposed secrecy on the part of the scientists, and of course later there was a government-imposed secrecy there. Well, as a result of the bombing of Pearl Harbor in December of 1941, of course, the nation geared up for war. And into our college, of course, we brought in courses in teaching fundamentals for the development of aviators, and the time was quite confusing. And at the end of that term, I received a call from Berkeley to come down there to be interviewed for an important project. I must confess that until I actually appeared for the interview, I had no idea what the project was. And as a matter of fact, during the interview, the only reference was to a project of national importance, and actually the word was used, the successful completion of this project would result in ending the war. So with that little information, I decided to take a leave of absence from the College of the Pacific, and arrived in Berkeley in June of 1942. And there, of course, I soon learned what the project was all about. And my first task in joining the project was to help out in preparing chemical compounds of uranium for use in the project. At that time, of course, we did not use the word uranium. The code word tuballoy was used instead. And so that we never discussed any of the compounds or any of the results in any terms other than compounds of tuballoy and percentage composition of tuballoy and so forth and so on. For example, if you wanted to refer to uranium dioxide, it was always tuballoy dioxide. So and another interesting thing was that the books containing the chemistry of uranium were actually removed from the shelves of the library, and they were sequestered inside the use of the project at the radiation laboratory of the university. One of my first jobs, which is probably pretty illegal, was to copy the reference book on the chemistry of uranium, and I did this at home using photographic methods, and it proved actually there was never a day that would go by where I didn't refer to this reference work. It was absolutely essential to have all of the knowledge of the chemistry of uranium as we progressed. Well, my first job, as I mentioned, was to take uranium tetrachloride in an impure form and distill it. Uranium tetrachloride is a solid material, and it distills only at high temperature, and a perfect vacuum must be used. So we had heaters at the bottom of our vessel, and then a cooled spot at the top, and then we would actually pump that down to a perfect, not perfect vacuum, but a very good vacuum, and start the distillation. Well, this sounds a little easy, but that was my first experience in vacuum leak testing, and that is a whole history in itself. But anyone who has done work in evacuating apparatus knows that there is an infinite number of leaks that can take place, and finding where those are really got to be quite a task. As a matter of fact, I was able to determine when I had plugged up a leak in the system sometimes by just listening to the vacuum pump, and the change in the clicking of the vacuum pump determined whether or not you were making any progress. Of course, we had very refined gauges to determine the ultimate vacuum. I believe those were called McLeod gauges at that time. Since that time, of course, the art of leak detection has really advanced, so that people have a very easy time of it these days. Well, I was able to produce this uranium tetrachloride in a pure form, and then we had to do this all in absolutely dry atmosphere, because uranium tetrachloride is very hygroscopic. And so we would do this inside of so-called glove boxes, which is simply a box, say about 3 feet by 3 feet by 3 feet, with a glass front, with holes cut into it, and rubber gloves sealed. And you would place your material in there, and then carry out whatever operations, either taking it out of the vessel where it had been distilled, or loading it into a vessel which was needed for subsequent operation. The subsequent operation, of course, turned out to be that uranium tetrachloride was the material to use as a source material for the so-called calutron, which was essentially a very large mass spectrometer. Now, the mass spectrometer, for those of you who don't know it, is a method by which you can separate isotopes into its component parts. And since uranium had two main isotopes, U-235 and U-238, you would place this uranium tetrachloride inside a vessel, which in turn was in a magnetic field, and then the vapor from this was actually ionized, and the uranium ions then were sucked out by means of an accelerating electrode, and they would go out into this space and be churned by the magnetic field, and by the time it reached the 180-degree point, it was separated into two components, the U-235 component and the U-238 component. When I joined the project, the most they had ever been able to separate up to that time was about 1 milligram of partially enriched U-235. And E.O. Lawrence told me that our objective was to make 80 kilograms of this material by July of 1945. Now, this was 3 years, and up to that time, and this had to be relatively pure, up to that time we had 1 milligram of that. Well, as you see, we had to make almost 1 billion times that amount in order to accomplish our objective. So we set out and solved the problems of making the uranium tetrachloride and making it pure, and I investigated then other methods for making uranium tetrachloride. And one method we had was to make uranium pentafluoride, which could be done by cooking uranium oxide in carbon tetrachloride under pressure and heat, and the conversion then resulted in uranium pentachloride. Then you had to take the uranium pentachloride and actually separate it into uranium tetrachloride and uranium and some other compound. At first it was thought that all we did when we heated this was to drive off chlorine, and so instead of having 5 chlorines, you'd end up with 4. However, I found that that if I were to do this carefully and distill it, there was a brown substance collected on part of the tube, and this brown substance turned out to be uranium hexachloride. Now, people had postulated that uranium hexafluoride could exist, but the size of the chlorine molecule would make it impossible to fit 6 around the uranium molecule. Well, so I had quite a number of skeptics on this, but I finally proved the point, and actually wrote up this as one of the discoveries of our group, and I was very proud to have persisted in proving that this could exist. Well, soon after that, we heard, and this was kept very hush-hush except for very few people, that the project was promising enough, and we went from a milligram to 100 milligrams to a gram and so forth, and after about a year, we were in the kilogram, almost in the kilogram state of the slightly enriched uranium, and so we were confident at that point that we could scale up the process, and consequently the decision was made to go to a site in Tennessee, which was subsequently called Oak Ridge, in order to carry out the big industrial scale-up that was necessary to produce the quantities necessary for our war effort. Well, one of the things that became obvious was that we needed 2 stages in order to carry this out. The first stage would bring the uranium up to an enrichment of about 12% and 88% U-235, starting with less than 1%. And then you had to take that material and put it through again, which would bring it up to 80 to 90%, which was what was necessary to make a nuclear weapon. So we had these 2 stages were called alpha and beta. As you can readily see, by the time the material got to be fed into the beta stage, the material had got to be very, very, very expensive. And so we looked at various and sundry problems along the way. My first problem that vexed us was the fact that when the uranium traveled in these large vacuum chambers and were collected in a collector, in a stainless steel collector, it was found that the material had high enough energy so it buried itself into the stainless steel collector, and it was impossible to dissolve it out by ordinary means. In our original experiments in Berkeley, we had put a stainless steel collector in a beam and collected some uranium, and then you took that stainless steel piece and used concentrated nitric, and it dissolved off beautifully. However, that was at considerably lower speeds, and so when you got to the high energies in the production plant, that uranium just embedded itself inside the stainless steel, and consequently only 30 to 50% of the material appeared as product. This alarmed people very much, naturally, and as soon as I saw this particular problem, I was fortunate to have on my staff a man who had had considerable experience in electroplating in industry, and I got the idea the thing to do is to actually electroplate with the copper, and then then the uranium would go inside the copper, but copper dissolves very easily in nitric acid, so you could bring the uranium into solution without any trouble. So we worked out the method of doing this. We set up electroplating baths, actually using the industrial sinks, which actually looked very much like laundry tubs, but we were able to do this in a very rapid form. And as a matter of fact, I can remember a conversation with E.O. Lawrence and told him of my findings on this, and he asked, I asked him, should we go ahead? And of course he said, I said, go ahead immediately. I said, we'll probably be able to put this in operation in about 2 weeks. And he says, I want every receiver that goes into these units electroplated by tomorrow morning. And we worked 24 hours around the clock, and sure enough, we were able to set up some lines so that we could feed some of these receivers in, and we didn't quite make the 48-hour deadline, the 24-hour deadline, but we were able to do this in about 48 hours, and we completely changed the process in that short a time. Well, this gave rise to some other problems, and however, at this time, I think I'll just stop here and see how this sounds so far. This is another test with additional lights. As a matter of fact, I have added a 150 watt floodlight immediately above the subject, so that I think we will get probably very much better and more even lighting with this. But there's no other way to find out but to test it. So I hope that this additional lighting will show up in the proper way, and if it works out, we'll have a much better setup so far as attempting to actually make documentaries of people in a more relaxed fashion. I think that also with this particular lighting, I think that it is much less obtrusive to the eye. But let's see what it looks like. We may not like it at all. So at this time, we'll cut and rerun.